Hello friends, in this video I'd like to solve the following problem from the International Mathematical Olympiad 1972, problem number 3, which was proposed by the United Kingdom. We wish to prove that 2m factorial times 2n factorial is divisible by m factorial, m plus n factorial for any non-negative integers m and n. So it's an interesting problem from number theory. Here are my hints. We will use the following lemma, which looks, maybe it doesn't look to be connected to the problem, but it is. We will prove that for every real numbers a and b, floor of 2a plus floor of 2b is greater than or equal floor of a plus floor of b plus floor of a plus b. And now, notice that our divisibility holds if and only if the p-adic valuation of this is less than or equal the p-adic valuation of this for any prime number p. And also, we have this nice formula for the p-adic valuation of L factorial. It can be written as the series, a sum going from k equals 1 to infinity of floor of L over p to the power of k. And also, p-adic valuation of a product is the sum of p-adic valuations. And that should be enough. So give this problem a try. All right, so first, let's prove our lemma because we will need it. Proof is quite simple. Proof. So let's write that a equals k plus x, and let's write b as l plus y, where k and l are integers and x and y are real numbers from 0 to 1. Then our inequality can be transformed to the following form: 2k plus 2x plus 2l plus 2y greater than or equal k plus x plus l plus y plus k plus l plus x plus y. Alright, and now notice the following: that 2k, 2l, k and l are integers. We can put them outside of our floor. And here also notice that what is floor of k plus x? It's just k. What is floor of l plus y is just l. Plus k plus l plus floor of x plus y. Alright, and after some cancellations, floor of 2x plus floor of 2y should be greater than or equal x plus y. And now, to prove it, I will consider 3 cases. Or maybe, you know what, no, I will do it graphically. Let's say, let's consider unit square with side 1, 1. Let's notice the following. Let's investigate the value first of x plus y. Well, if x plus y is less than 1, this floor is 0. And notice that this line, this diagonal, is exactly the line where x plus y equals 1. Alright, so on this part, our triangle, on this part, but without the diagonal, the value of this expression is 0, and on this part, it is 1. Alright. And what about the left-hand side? What about the left-hand side? Let's see. I will divide my unit square into 4 parts. Along the lines 1/2, 1/2. And notice now the following. When both x and y are less than 1/2 on this part, the value of this expression is what? It is 0. Alright. On this part, on this square right here, well, x is between 1/2 and 1, so floor of 2x is 1, floor of 2y is 0. So here we have value of 1, and likewise on this square right here, the value is also 1. And finally, on v square, where both x and y are greater than 1/2, the value of our sum is 2, because it's 1 plus 1. And now clearly, on every part of our squares, this inequality holds, because, let's put it right here, on this entire thing, on the right hand side we have 0, and on the left hand side we have either 0 or 1. And on this upper triangle, we have either 1 or 2 on the left-hand side, and we have just 1 on the right-hand side. So our lemma was proved, has been proved. All right, and now let's go back to our actual problem. Now, we wish to prove that n factorial, m plus n factorial divides 2m factorial to n factorial. Notice that this is equivalent to saying that for every prime p, the p-adic valuation of m factorial, n factorial, m plus n factorial is less than or equal the p-adic valuation of 2m factorial to n factorial. If you wonder what is the p-adic valuation, well, it's the highest exponent such that p to this exponent, p to this power, divides our number. So for example, let me give you an example. Number 12. What is the p-adic valuation of 12? Well, it is 2, because 2 squared divides 12, but 2 cubed does not. And likewise, the valuation with p equals 3 of 12, it's 1, because 3 divides 12, but 3 squared does not. All right. And now, notice that, of course, the p-adic valuation of a product is the same as the sum of p-adic valuations. So this should be true. Less than or equal p-adic valuation of m factorial plus n factorial. All right, and now we will make use of a fact which is well known, that p-adic valuation of L factorial can be expressed as the following sum from k equals 1 to infinity of L over e to the power of k. And using this formula, we have the following. We wish to prove that for every prime p, well, and here we can write sum as k goes from 1 to infinity. And notice that we can combine these three sums into one. So we have m over e to the power of k plus n over p to the power of k plus m plus n to the power over p to the power of k. This should be less than or equal the sum as k goes from 1 to infinity. Also, let me make it a little bit smaller. Of 2m e to the power of k plus 2n e to the power of k. And now notice that this inequality is true in because of our lemma. Because here we have something of a form floor of a, floor of b, floor of a plus b, less than or equal 2a to b. Yes. So since every term of a sum on the left hand side is less than or equal every term of this sum, after adding these inequalities together, we also get an inequality which we want. And this really closes our problem. So as you have seen, p-adic valuations can be very, very helpful. So yes, and that is it. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.